Welcome everyone. Let's move on to section 1.2 of our textbook Discrete Mathematics Elementary and Beyond by Lazlo Lovasz. So this section is about sets. Sets, as you know from our high school. So this is the fundamental structure in our mathematical studies. So as you know, the typical definition about the sets, that it's a collection of objects that we collect them because of certain relationship they hold among themselves. So for example, from our last section in which we were discussing about a party in Alice home, so Alice and her friends, Alice, Bob, Carl, Jan, Eve, Fred, George, A, B, C, D, E, F, G. So we can represent these participants of the family with the help of a set. So let's call this set as P. P is collection of these objects that we are discussing, these people. So P for example, people are persons. So we can represent them uh, as set like Alice, Bob, Carl, Jan, Eve, Fred, George, or we can represent through a different notation. But important thing is the meaning should be conveyed properly and exactly what we want to discuss about. For example, we can say Alice and her guests in her home, or we can say Alice and her friends in Alice's home. So different people may give different notation for the same objects, but important thing is the message should be conveyed the same. A person who read one notation of the sets or other notation of the sets, he should get the same message. So we can define some other sets. Let's call them subsets from our main sets. So the main set in which we collect all possible elements, individuals, objects in one set. So usually we call it our universal set. So we can define some subsets. For example, we have a set of girls. Let's call it G. So G is such a set that it's like girls in the party. So we can also represent it in more abstract, more mathematical way, like X belong to P and X is a girl. X belong to set P that we have defined above, and within this set X is such an element that X is a girl. So we have to see who are the girls in this bigger set P. So Alice is a girl, Bob, Carl are not girls, Diane, Eve are girls, Fred and George are not girls, they are boys. So Alice, Diane, Eve, they are girls, so we collect them in one set. G is equal to Alice, Diane, Eve. So G is a subset of our set P. We can define another set, let's call it D. So X belongs to P and X is over 21 years of age. So we list down the ages of all participants who has what age. So we can see who are elder than 21 years of age. So we can see, for example, Alice, Carl, Frank, they have ages more than 21 years of age. So we can collect them like Alice, Carl, Frank, they are those participants whose age is more than 21 years of age. We can perform different kind of operations on the set. So for example, if we want to see that that participant in this party who is a girl and who is more than 21 years of age. So that means we have to take intersection of G and D. We want to find the common element, common person in the set G and D. G is the set of girls, D is the those participants, set of those participants who are more than 21 years of age. So who are common? Alice, Diane, Eve and Alice, Carl, Frank. So obviously Alice is the common. So Alice is that person who is girl and who is 21 years of age. Before discussing about more operations on the set, so let's see about the number sets. We are familiar with the number sets. We are using in we have been using it throughout our, like, from class 1 till now in our daily life. Every time we are playing with the numbers, so we use many number sets. For example, so we have set of positive integers. We have integers, and among these integers we only takes positive integers. So we can define it like X belongs to Z, Z set of integers. such that x is greater than 0. So x is a positive integer. Or we can define another set of non-negative integers. So x belongs to z and x is greater than equal to 0. So when we talk about non-negative, so we need to include 0 as well. 0 is neither positive neither negative, it's neutral. So when we talk about positive integers, we exclude 0. When we need to include 0, at that point we say non-negative integers, all those integers which are non-negative. Similarly, we can define set of non-positive integers, means all those elements which are negative and 0. So x is less than equal to 0, we can define like this. And then we have number of sets, like if we go in the sequence, so empty set, there are no elements. Then we have natural numbers 1 2 3 4 5 6 7 8 and so on. And then positive integers, so actually natural numbers are set of positive integers. So natural numbers is same as set of positive integers, so it's a proper subset. So set of positive integers is subset of integer sets. Integer sets are subsets of rational numbers, those numbers which we write down in the form we can write down in the form of fraction like p over q. And rational numbers are subset of real numbers. Real numbers are subset of complex numbers, and we can keep on extending. Complex numbers may be subset of three-dimensional numbers, and then four-dimensional, and so on. We can keep on going like this. So we all know about number sets. We have been using in our daily life, in our mathematical studies. Every time we have been using. Let's talk about operations in set. Set operations. Again, we are familiar with these operations. So we talk about unions, we talk about intersections, and then we talk about differences in the sets. So let's see, union A, union B. So it means if we have number of elements in set A and number of elements in set B, so A union B is a set in which we include elements of both A and B. In intersection A intersection B, so we will take only those elements which are common to A and B. Different sets, like we have A minus B, we also write it down like A slash B. So A minus B, difference of A to B is like those elements which are present in set A but they are not present in set B. Similarly, we can define B minus A as difference set B minus A, those elements which are present in set B but they are not present in A. And then we have something like symmetric difference. So symmetric difference is actually union of A minus B and B minus A. We see that two sets A and B, at what point they are different from each other. Let's take an example. So for example, we have two sets. A is equal to A, B, C, D, E. We have 5 elements here. And B is a 3-element set. B is equal to B, D, F. So if we want to take union, so it means we will take all elements in set A and all elements in set B. So remember, in sets, we do not repeat elements. So if one element is included, we don't have to write it again. And order doesn't matter. It doesn't matter in which order you write the elements. So A union B is all elements of A and then all elements of B. So A, B, C, D, E, F. So we get all elements. That's fine. And next is intersection. So we have to see which elements are common in A and B. So common elements A, B, C, D, E and B, D, F. So we can see B is common and D is common. So A intersection B, it should be B, D. A intersection B is B, D. Common elements. So next is the difference set. So A minus B, we want to see what is the difference between set A to set B. So A minus B, those elements which are present in A but they are not in set B. So A, C, E are those elements which are in A. B, D we cannot include because these elements are present in B. So in a way you can see A minus B is we take set A and we exclude A intersection B out of it. Those elements which are common between A and B, so we do not include in A minus B. Similarly, we can define B minus A. So those elements which are present in B and which are not present in A. So we should not include those elements which are common between A and B. So B minus A, we can see BD are common between A and B. BD from these are present in B, these are present in A, so this is not the difference. F is an element which is present in B and it's not in A, so we have to write down B minus A is equal to F. So this is the difference, A minus B and B minus A. So next is symmetric difference, A and delta B. So this is a union of A minus B and B minus A. So we simply combine the elements in A minus B and B minus A. So this is A, C, E and F. So A delta B is A, C, E, F. And we can see it in another way, that we have set A, we have set B. So we see at what point they are different from each other. So at point A, at element A, they differ from each other. B, they are common, so we should not include. C is something different, it's a difference between the two. D is something common, we should not include. E is something different, and F is something different, so we include these elements. A delta B we can represent in another way, like A union B minus A intersection B. We take the union of the both sets and then we subtract those elements which are common to each other, so we will be left with only the difference. So over here, important thing to note about the differences is A minus B is not equal to B minus A. A minus B is not equal to B minus A. However, symmetric difference, A delta B is same as B delta A. That's why it's called symmetric difference, because it doesn't matter you take A delta B or B delta A. We just have to see both sets are different at what points. One important property about set operation is De Morgan's law. So this is like a distributive property of intersection over union or union over intersection, we can see. So we can have two laws of De Morgan. So A intersection B union C is same as A intersection B union with A intersection C, and the other is A union B intersection C is same as A union B intersection A union C. We can prove it. There could be different ways to prove. One simple way to prove is using Venn diagram. So often we prove the properties, simple properties of sets using Venn diagrams. In Venn diagram, we represent our sets with the help of some circles, depending upon the case property that we are going to prove. So they might be intersecting, they may not be intersecting, like this. So in general, we draw them like they are intersecting to each other. So we try to prove like the first law using Venn diagram, and the second law will be very much similar. So second law you can prove easily. The first, I'm going to just describe proof of the first part of the De Morgan's law. So let's see the first part. A intersection B union C is equal to A intersection B union A intersection C. So let's take the left hand side first and then we move to right hand side. So in the left hand side, first we perform this operation B union C. So over here you can see in the shaded area in the blue, so this is B union C. So all set B and all set C is included, so this blue shaded area is B union C. And then we have to take its intersection with A. So which areas are common between B union C and A? So these are this highlighted area in blue. So this is A intersection B union C. So the left hand side part we have shaded over here. Please keep this picture in your mind, and then we show the right hand side. So this is first A intersection B. So we take intersection of set A and B. So this is shaded over here in the blue. And then we take intersection of A and C. So this area is shaded in blue over here. A intersection C. So now we just have to take union of the both. So we will get this right hand side. So we take union A intersection B union A intersection C, so we get this shaded area in the blue, and it's same as we have got in the left hand side. So left hand side is same as right hand side. So similarly we can prove the second part of De Morgan's law. Over here I want to discuss something important about graphs. We looked at these graphs in our last lecture when we draw graph of handshaking scenario. So graphs as we discussed before, we represent in certain problems, certain scenario, our different elements with the help of nodes, and if they have certain relationship between them which we are interested in, with the help of edges. Over here I have drawn a simple graph on 6 nodes, 1 2 3 4 5 6. So graph can be represented with the help of sets as well. So we represent graph, for example, let's call it G. So G is graph is a structure which is described with the help of two sets, set V and set E. V is set of vertices and E is set of edges. V is set of vertices and E is set of edges. So over here we can see we have 6 vertices. So we denote these vertices by V1, V2, V3, V4, V5, V6. So set of vertices, V is collection of 6 vertices over here. And then we define certain relationship, which is those relationships are represented with edges. So let's denote these edges. Let's name them. So we have E1, E2, E3, E4, E5, E6, E7. So we can represent these edges in a set notation. So let's call set of edges E is equal to E1, E2, E3, E4, E5, E6, E7. That's fine. So if we have this figure in front of us and then we have named these edges like this, so we can simply write it down E1, E2, E3 and so on. In this case till E7. But if we want to specifically describe which edge represent relationship between which two vertices, like over here E1 is edge between vertex 1 and vertex 2, E2 is an edge between vertex 1 and vertex 5. So this can be represented in more elaborate way. We have an alternate way to write edges. So we write edges like a pair of vertices. So pair of vertices v1, v2. So this is the first edge. So the between vertex 1 and vertex 2 there is an edge. v1, v5. So between vertex 1 and vertex 5 there is an edge. v2, v5. There is an edge between vertex 2 and vertex 5. v2, v3. So an edge between vertex 2 and 3. v3, v4. An edge between 3 and 4. v4, v5. So there is an edge between vertex 4 and vertex 5. And v4, v6. An edge between vertices 4 and 6. So more specifically, E1 is v1, v2, and then E2 is v1, v5. Edge between v1 and v5 we named it as E2. E3 is v2, v5. E4 is v2, v3. E5 is v3, v4. Edge between vertex 3 and vertex 4. E6 edge between vertex 4 and 5. E7 edge between vertex 4 and 6. So this notation, it exactly tells us edge is present between which two vertex. Over here we are talking about simple graphs in which there's no direction. So when there's no direction, so it doesn't matter in which order you are writing the vertices when you are representing the edges. For example, v1, v2, the first edge, it is same as v2, v1. But if there is direction, then we have to be careful. We will talk about the direction later. So over here there are some exercises. So I will request you people do it by yourself. So for example, list all subsets of a set 0, 1, 3. So we have 3 subsets, 3 element set. So we will have how many subsets over here? So I give you the answer. 2 raised to power 3, 2 raised to power number of elements in the set. So 2 raised to power 3 is equal to 8. We will get 8 subsets. Which subsets these will be? So please list down all those 8 subsets starting from the empty set till we have complete set 0, 1, 3. So empty set, single element sets, 2 element sets, and 3 element sets. Then second one is list all subsets of A, B, C, D, E, and with condition that containing A but not containing B. So although this is 5 element sets, but with the given condition, we have reduced our free elements that we can choose. Not containing B, so it means subsets that we are going to list, B is dropped. So effectively B is not present. And A must be there. So whichever set we are going to take, we have to place A. So an easy way is in the beginning you can just take CDE where we have choices. CDE, it will become a 3 element set. List down all the subsets of CDE. And condition is it should not contain B. So we have taken B already out. It should contain A. So with the CDE 2 raised by 3, 8 subsets that we have listed now, we should put A in each and every set because A must be part of it. A must be part of it. So we just simply place A in every set. So number of subsets will remain the same, 8 subsets, 8 subsets. CDE are our free elements which we can choose easily, freely, and we place A in every subset. Third question is define a set of which both 134 and 035 are subsets. We can define infinite sets for this thing. Define a set for which both 134 and 035 are subsets. So take the union of both sets and after that we can append any kind of elements. So 0, 1, 3, 4, 5 and after that we can have, we may or we may not have more elements, but 134 and 035, these elements must be there. And then the second condition, if we put this constraint that find such a set with the smallest possible number of elements. So when we put this condition, the smallest possible number of elements, it means now we cannot put additional elements at our will. So we have to keep only these sets which are given 134, 035. So just take the union of both. So it will be 0, 1, 3, 4, 5. So this is the minimum possible number of elements of which both these sets 134 and 035 are subsets. So over here we stop. Thank you very much. Shukriya. Maxi.